So last section of Chapter 2, we're going to graph linear inequalities and also absolute value inequalities. This should be able to go pretty quick because when we graph these, we're going to graph it pretty much as if it is a line, but then we just have to make a couple decisions based on the inequality, whether that line should be dotted or solid, and then which side of that line do the solutions lie on. So we need to shade one side of the graph or the other. So if you're not sure what I mean when we talk about inequalities, here's what we're going to be graphing. It's something like y equals, or sorry, not y equals, that's an equation. Y is greater than 2x plus 1. So on the coordinate plane, what points could we pick where if we plug in x, 2 times x plus 1 is greater than the y coordinate? Well, it's pretty simple to deal with. All we have to do is graph it like it's a line. So we're going to basically graph the equation y equals 2x plus 1, so a slope and a y-intercept. But we have to be careful when we draw the line, because if it's less than or greater than, we don't want to include the points on that line, because those are the ones that make it equal, and we're not including those with this inequality. So we would draw a dashed line for greater than or less than, but we would keep it solid if it's equal to, because that line would be included in our solution. Then we need to test a point that's not on the line and shade that side of the graph. In a lot of cases, the easiest point to use is 0, 0, and I'll show you why that's simple to use. Or there's another little cheat that we can use here, and I'll talk about that as we go through an example. But let's look at this one first. So we have y is greater than 2x plus 1. So we have a y-intercept at 1, right? Y-intercept at 1, a slope of positive 2, so up 2 over 1, down 2 over 1, right? So, and then a dotted line. Since we're not equal to, we don't want to include that line. So then what we're going to do is test a point on either side and see if it works. And the easiest point to use in most cases, I would say, is 0, 0. It's going to be the easiest to use unless it's on the line. Then we have to find something else. But the reason this is easy to use is plugging in 0 just makes things pretty simple. Because if we plug in 0 for y, well, that's just 0. If we plug in 0 on the right, that goes away and we have 1. Now, is the statement 0 is greater than 1 true? Is that a true statement? Is 0 greater than 1? No, it is not. So 0, 0 is not a solution. So the solutions must be on the other side of this inequality. Okay? So any point over here, if we plug that in, then that would satisfy this inequality. Okay? So here's another cheat that we could use instead of plugging in 0. If we have y is greater than, we want the y-coordinates that are greater than the y-coordinates on this line. So we would shade above that line. If we had y is less than, we would want the coordinates that are less than that line, and so we would shade below. Now that only works if it's in the form y is greater than or less than. Don't try doing that if it's rearranged some other way. Okay? But there's another little trick that we can use when we do these. So we'll do just a few simple examples together. 1, 2, 3. Let me just get the graphs drawn. So here we have y-intercept of negative 3, slope of 1/2, so up 1 over 2, up 1 over 2. It's less than or equal to, so we're equal to, so we want to include the solutions that are on those lines because those make that inequality equal. And then we could either just say, well, y is less than the points on that line, so we're going to shade below. Or again, if we plug in 0, 0, we would have 0 is less than or equal to negative 3. Is 0 less than negative 3? It is not. So our solutions must be on the other side that 0, 0 is not on, so we would be below. Here's a case on example 2 where we would need to test a point. So on this one, let's use that little method where we will find the x and y intercepts. So let's find the y-intercept first. So remember a y-intercept, we have 0 for x, and then it's some y. So if I plug in 0 for x, that 3x goes away. Divide both sides by 4, and y is going to be 3. So our y-intercept is at 0, 3. Now let's do the same thing the other way. To find the x-intercept, it's some x, and then 0 for y. So we plug in 0 for y, and that goes away. Divide both sides by 3, and our x-intercept is at 4. So we can connect those 2 points with a dotted or solid line. Which one? We would use a dotted line because it's just greater than, not equal to. And then we can't tell from here whether we need to shade above or below. So we need to actually test a point like 0, 0. But 0, 0, again, is pretty simple because if we plug in 0, both of those terms on the left are 0. So we would have 0 is greater than 12. Does that work? It does not. So we have to shade on the side above our line. Lastly, we could do absolute value inequalities. So again, we're just going to graph what we have as if it were an equation, but then we have to shade based on information about that graph. So here we have y equals, or y is greater than the absolute value of x minus 1. That x minus 1 moves us right 1. So our vertex is moved over 1. And then our slope is 1. So it's going to look like that, except not like that because we need to use dotted lines going over 1, up 1, over 1, up 1. And I'm kind of just speeding through that. Right? But then would we shade above or below? Well, again, our little cheat, we have y is greater than, so we want the values above that line. The other option, if we plug in 0, 0, we would have 0 is greater than absolute value of 0 minus 1. 0 minus 1 is negative 1. Absolute value of that is 1. Is 0 greater than 1? It is not. It is not. So we would shade on the side opposite of that 0, 0, so the part that's up and or above and inside the absolute value. And that's our solution.